All right. What do you notice about the size of this answer compared to your previous answers?
Very small.
Way smaller. Why? Okay, well, what's the difference? Yeah, you just want to know how many groups you can pick when you aren't trying to make all those different patterns out of those people. Way less choices. So combinations are always going to be considerably smaller. Now, in reality, what is your calculator doing when it calculates these? This is the formulas that you're asking about on the back of your journal. What is your calculator actually doing when it does NPR versus NCR? What it's actually calculating is it's doing n factorial. And if it's a permutation, it's subtracting the two numbers and dividing by that factorial. If it's a combination, it's got to get smaller numbers. So if it's going to be smaller numbers, what do you think is going to happen to make the number come out smaller? So you have to get more on the bottom. And it turns out it's exactly the same, except on a combination, it also divides by the R factorial. It divides by two numbers factorial when it's calculating it. And I'll show you what that means in terms of numbers. If we did, which ones do I have here? Okay. If I did 7P3 versus 7C3, what's the difference in how it calculates? What's it going to put on top? 7 factorial. Then it's going to subtract the two numbers and divide by 4 factorial. That's what it's doing. When it does 7C3, it does the 7 factorial, it subtracts them and gets 4, but it also takes the 3 that you have there and does that factorial. I always remember on combinations, the two bottom numbers have to add up to the top number. But doing them all is factorial. Okay, now, are you guys going to have to calculate it that way?
No.
No, because your calculator will just let you plug in the NCR, the NPR. Okay, but scholars, bull people, you might see somebody ask something like this, have you calculate one by hand. And knowing how to do it is fairly easy. Now, let me point out, for example here, I need more space. Okay, if I was going to do this, in fact, here, I'm going to stand here as we go through this whole chapter, and I'm going to calculate combinations in my head. And the question is, how am I doing those combinations in my head? Because I guarantee you, I'm not figuring out each of these factorials, multiplying them together, and dividing them.
How are you doing it?
Much easier way. What I'm doing is I'm going, oh, look, 7 factorial is 7, 6, 5, 4, 3, 2, 1. 4 factorial is 4, 3, 2, 1. And I am crossing off, exactly. I go take the biggest number and I cross it off because I know I'm going to lose all those. So now all I'm left with is 765 over 3, 2, 1. I know 3, 2, and 2 times 1, I know that's 6. So when I'm doing it, then I go, oh, look, those cancels. That cancels the 6. 7 times 5 is 35. I can do that in my head if I think about what's going to cancel. So you can work lots of these combinations, permutations. If you know the little bit of formula, you can work it by making cancel. You just write them all out and you start canceling. So 3 times 2 times 1 is the same thing as 6. Yeah. So you can get a lot of, you know, if it's big numbers, no, you can't do it. But if I stay in single-digit numbers, I can do a lot of them in my head because I think about what cancels. Okay. Whoa, dudes, I don't want that page. Goodbye. That's not dealing with that right now.
Hey, hold on, I didn't have that all.
What? That? Yeah.
So you just find out what the 3 times 2 times 1 is, which is 6. And then
Yeah. Sometimes, that one happened to be 6. Sometimes maybe I'll cancel the 3 into one number and the 2 into another number. You just start canceling as much as you can and multiply what's left. That's all it pretty much takes. Okay, so now can I roll screens? Yes, I can roll screens. Actually, I take that back. Maybe I do need part of that back. I don't really want to do that. Let's go play here with something was coming up here. We just had Easter. You got candy in your Easter basket. It had 7 Peeps, 4 Reese's eggs. Oh, you know those dumb marshmallow. Yeah, I don't like them, but some people are into Peeps. I'm not a Peep fan myself, but okay. Marshmallow bunnies? We can't have caramel stuffed bunnies. Hi.
Chocolate bunny. Chocolate bunny.
Cream eggs.
And 3. I should have made them all the same shape though, but okay. So, you get to blind draw, you get to pick 4 pieces of candy. You can't see them, you're just going to pick them.
Go by Gail.
Okay, I want to know how many combinations are there with, what do you want? What did we want to eat? Okay, 2 eggs and 2 bunnies? Okay, so how many different groups could you pick that are simply have 2 eggs and 2 bunnies? Now the question is, how do I pick 2 of these and 2 of those? You do the combination separately. You go, okay, first of all, why is it a combination and not a permutation? I don't care what pattern I pick them in. I just want to grab them. I don't care what order they get picked in. So I'm going, all right, I got to pick 2 eggs. How many eggs are there to pick from? 4. So you would pick, from the 4 eggs, you would pick 2. And now I got to pick 2 bunnies. That's a separate combination. How many bunnies are there? 3. And you're going to pick 2 of them. And then, since I want to know both together, I'm going to get a number here. This is going to be 6. That's going to be 3. And what I do, it's not keeping up with me. Combinations. Okay, all you do is you figure each number and you're going to multiply them together like we've been doing in every other problem. So there would be 18 different groups you could pick. Okay, that's combinations. Combinations are usually, the biggest problem we have with combinations is deciding, am I picking groups or is it permutations I'm picking patterns? Because doing the combination problem is pretty simple. I'm going to come back to this here in a little bit with probability, but we got to go talk probability a second, and then I'm going to come back and use this example. All right. Probability. You have seen this before. I did this with you at the beginning of the year because it was on the math assessment, so this should not be a big surprise. Probability. Okay, every book, every teacher uses different words. I was always taught successes over total. Ways to get what I want over total. That can be total outcome. Some of you learned desired over total. That's another way you can write it. Whereas odds, and that's the issue, hopefully we all remember, odds is, I prefer ways to succeed over ways to fail. Some people do desired over undesired. Most people in the real world do not realize there's a difference between probability and odds. They just don't know that that difference exists. Okay, so I'm going to ask you here, no yawning. Okay, if I tell you the probability of rain today is
92%.
Oh, that's 70. Actually,
I was
three
gonna
and
say
Here, let me check real fast.
3 out of 5.
Oh, that's wrong.
Okay.
That is very wrong.
Tell me what the odds of rain today is.
8 out of 5.
32.
Because this was 3 ways to succeed over 5 total ways. To do odds, you need to have the ways to succeed over the ways to fail. So how many ways are there to succeed?
3 to 2.
3 to 2. Thank you. Okay. So on probability, the top number can never be bigger than the bottom number. But on odds, it certainly can. You can have a greater number of successes over failures. So there is a distinction between them.
You wrote the word that you say we can't say in this room.
No, I didn't spell it out with the other word, letter.
Exactly like that. Right.
Yeah, like you didn't know. Okay, there are 2 kinds of probability. Hint, this was on your journal. There's what we call theoretical probability, and there's what we call experimental probability. Okay, what we do in math class is theoretical probability. Well, what we just did there, when we look at what should happen, we're doing theoretical probability.
But what does happen?
So when you do theoretical probability, you're calculating it using formulas, known formulas. We know how to calculate these things. Mathematically, this is what the probability should be. We know that's what's supposed to happen. Is that always what happens?
Nope.
Not necessarily. That's just, theoretical probability works if you assume you're doing it thousands of times. You can do something repeatedly over and over and over, the probability is going to hit the theoretical probability. Obviously, luck comes into play. Chance comes into play. If you only do something once, yeah, it may defeat the probability. Maybe it happened when it shouldn't have. But theoretical assumes over thousands of times that's what would happen. Okay, experimental though, sometimes we don't have a formula. Sometimes there are situations we just don't have a formula to calculate that probability. So instead they'll do what we call experimental probability, which is, maybe, if it right, when you perform the activity many times and see what happens. Seriously. So sometimes we can all roll a die, and you all know the chances if you roll a die, the chances that you will get. Actually, if you roll 2 dice, we'll do it that way. If you roll 2 dice, which number should come up most often? Which number on when you roll 2 dice, which number can come up the most?
Oh,
There's more combinations that make that number.
Oh.
6.
Nope.
12.
Obviously, none of you are craps players.
2.
7. There are more combinations of 7. You can make 7 with 3s and 4s, 2s and 5s, 1 and 6. So there's more chances of getting a 7 on when you roll dice than anything else, because there's more combinations that will go together and make a 7.
6 should come up the most, though.
Okay, but if you actually sit there and experimentally roll 2 dice 100 times, are you going to land with the exact number, how often you should get a 7, how many times you should get a 6?
No.
No, because chance goes into play. You can do probability experimentally. If you're going to do it, though, you need to do it thousands of times. So you take out the fact that lucky streaks happen. You have to do it enough times that you eliminate those lucky streaks and you get down to more exact results. But we can predict probability by simply doing it over and over and over and over and over and see how often it happens. Thank you.